Just so hello all. So today we are going to talk about like a paper, deep probabilistic programming, basically it was proposed by Dustin Tran and others basically. So here let's talk about that. So before jumping into like the probabilistic programming, so let's understand like or get an overview of what the standard deep learning paradigm is like in a way. So we all know that standard deep learning paradigm is basically you're using state of the art applications nowadays like computer vision, natural language processing, and in speech recognition areas. So and applications can be like transformers like GPT-2 model and so on like that with different other models as well. And all of this is possible because of the like complex neural architectures like yes, ranging from simple to complex such as feed forward neural network, recurrent neural networks, convolutional transformers, and so on like that way. And we are training this like huge neural networks is possible because of like stochastic gradient descent backpropagation dropout like that way, which kind of adds as a way of regularization as well, and like kind of enables us to train this deep neural network models with massive data sets here. But we all know like this works very well, but like what are the issues here with this particular paradigm, like sort of non-Bayesian deep learning in a way, like standard deep learning what we call it. So here the major issue is sort of it computes the point estimates, like so in this case we get a point estimate that is a fixed value. We don't get a error uh, boundaries, basically kind of how certain kind of a prediction is sort of in a range. So that kind of boundary estimations is not possible. Next is it also kind of overly confident. Over it is also overly confident. That means sometimes it kind of predicts the wrong classes with also high probability, like with higher confidence in a way. So that is the one major issue. Other we all know is overfitting. So like this deep neural networks are prone to overfit. That is also one of the issues. And next is like basically dealing with all this hyperparameter tunings and kind of finding out the best optimal model here. So these are all the issues basically that we face in normal like standard deep learning basically here. But now let's see what basically we get when we switch to probabilistic machine learning here. So for probabilistic machine learning, we can consider it as a joint distribution. So basically it means like there is some observed variables X, like the observed data that we have, and also there is some hidden variables Z. So you can think of like basically your the probabilistic model is a joint distribution of both. So basically in a way you can think of it as like a hidden variable Z that leads to some observed variable X in a way, sort of. So here it is sort of a probabilistic the joint distribution P of Z comma X here. And in this case here the inference basically about the hidden variables is basically through the posterior. So as we all know, if we by the formula of conditional probability or like definition of conditional probability, so conditional equal to the joint upon marginal sort of. So P of Z given X, that is equal to nothing but the joint probability of hidden variable Z and observed variable X upon the marginal P of X, or we call it as posterior in a way. But here this posterior is intractable because like your inference is intractable because of this denominator term. Because in a way, if you see like if we already know the distribution of X, then we wouldn't have like we would not be doing this machine learning. Uh, we would not be training a model because the main objective of like doing a probabilistic model is basically you're understanding sort of what the distribution of the observed variable X is like in a way. So for this particular inference part, so what we come up with is sort of variational inference. So here we do it, what we do is sort of an approximation. So we know that we cannot basically find the exact posterior in a way, but what we can do is sort of get to the exact posterior as close as possible. So what we do here is sort of we assume sort of a distribution posits a distribution like variational distribution of families, let's say a Q, and that is sort of a close to the exact distribution that is a posterior, and we try to get as close as possible to the posterior, true posterior in a way, sort of. And this is done by minimizing the KL divergence, sort of like KL divergence is basically finding out the uh, difference between the distributions, and we try to get minimize this divergence and move close to the true distribution here. So like we got to know about what probabilistic machine learning is. So now like let's talk about like probabilistic programming. So probabilistic programming in a simple way is sort of like the programs that generate sort of samples like or inference in a way. Like so whatever we saw like sort of a models that generate sort of some samples are known as probabilistic uh, basically programming in a way. And you can think of this probabilistic programming as a way of automating the inference of the unobserved variable in the model condition on the observed variable. So that means here like basically we are trying to automate the inference part of the model, but basically that particular inference part is conditioned on the output date, like the observed variable that we see. So here it's sort of a cycle of simulation and inference in a way. And there are many probabilistic programming frameworks such as Church, Venture, Angelican, Stan, Pi, MC3, Edward, and so on like that way. So each of these probabilistic frameworks have its advantages and disadvantages. But today we are specifically going to talk about Edward here.
A couple of questions, if you're willing to take them during, or if I should say them after.
No, no, yeah, you can like say it now as well. Like, so.
Okay. You talked about inference over these hidden variables, or like
Which one? Which
for the
slide?
unknowns. You talked about it twice in the slide after this one,
Okay, this one, yeah.
um, and you also mentioned it on the P of x comma z slide.
Yeah.
So why do we care about these hidden variables?
So here we assume sort of there is some hidden variables, and that hidden variable, so there is some random generating process, basically, which basically from which the hidden variables pass through, and we get the exact observed variable in a way, because we don't know the exact distribution of the observed variables. So we assume there is some distribution like let's say Q, from where the hidden variables come, and there is some process that generates the observed variables, which basically with Z as the input in a way. You can think of like that. Maybe if it's too complex.
That's a fair explanation. So the hidden variables describe some sort of data generating process, and
Yeah,
knowledge of that allows you to have more insight into how your data came to be.
yeah, like to get more insight about the exact distribution of the observed variables.
Sounds good.
Okay. Uh, yeah, Josh can continue.
Yeah, so we will look into some applications first, or rather case studies. So the first one is regarding a taxi case study. Can you go to the next slide, Jay? Hello. Yeah. So in this, we had a data set which was taken from taxi rides in the city of Porto. So this data set basically has 1.7 million taxi rides, and how they collected this data set was basically each taxi sent its location in form of coordinates like x comma y every 15 seconds, and then so the aim of this case study was to cluster the trajectories and find the hidden patterns in the taxi rides. So if we were to take the path of general statistics, what we would do is we would take a subset of data and then would apply summary statistics, or like some simplified model for analysis. But here we take the full data set and use probabilistic modeling for analysis. So on the right, you can see those two images. So what we find is that trajectories have structure. For example, like most of the taxi rides took some major roads or highways which appeared very frequently. So this motivates us to first identify like the lower dimensional representation of the data, and then we can cluster the representation according to that. So they have used principal PPCA, which is probabilistic principal component analysis for this. And as you can see on the left image, that they have tried to cluster the taxi rides, and the different colors represent the different clusters here. Can you go to the next slide? Yeah, so the second case study was regarding effects of genetic measurements. So here, what we were interested in is to find.
Before you get into this, sorry, I had a question about the previous slide.
Yeah. Yes.
So you're saying the what on the left you have the final visualization, not the initial one, right?
Yes. Yes.
And so like what is A and B? Like A and B are divisions. Like if you select only two clusters, is that the top two principal components?
Yeah, so first, like what they did was they took the data set, found some inferences, and then again inculcated that their findings into the next model. So initially, what they found was the rides which took the inner bridge were shorter, as you can see on the first image in the right side. Uh, the ones that used the inner bridges were shorter and they were confined to one particular area. And on the B image on the right side, the ones which took the longer bridges were spread apart and were from one basically from one part of the city to another part of the city.
Okay, and the point of this paper is to say that look, you can do this using probabilistic programming. Is that it?
Yeah, and they also wanted to show that basically this application was initially done using Stan,
Mhm.
and they tried various applications like the ones I am going to mention now, two more applications, and they wanted to show that Edward is very flexible and you can do everything with Edward. But as compared to other probabilistic programming languages like Stan, for example, you can only do one application. I mean, it is not generalized enough.
Okay, fair enough. So they, yeah, I mean, they wanted to give you some
Yeah,
case studies of look, here is how we use these things.
yeah. So basically, with Edward, there are two goals in mind. First one was flexibility, and second one was making it computationally efficient. So here they are showing flexibility part where Edward is like applicable to many models and applications.
Okay, that sounds good. That's thank you. Oh, by the way, like people can jump in and ask questions. Like doesn't just have to be me. And especially like clarifying questions where you didn't understand something, especially this is a small group. We can actually address all of your doubts and sit and discuss them if you didn't understand something. Sorry, go ahead.
Yeah, so in this case study, what we are interested is finding causality here. So we want to understand how genetic factors in we have a in this data set of 1.6 billion measurements. So for example, metabolic levels arise from your genome, right? And some specific diseases are also caused by certain genetic factors in a genome of a person. So they wanted to like analyze and find traits in this. So as you can see here, there are different colors which represent different like ancestral backgrounds and the types of bondings in the genome. And according to that, they want to find things like what affect how does it affect the metabolic levels of a person and stuff like that. So by using Edward, they have tried to show that you can understand the cause and effect from this genome data. Mm. Can you go to the next slide? So this is the NBA case study where you had the data set. The data set basically had a bunch
Okay,
of
sorry
individual
again.
points on. Yeah.
Question about the previous one. I'm not sure if everyone else understood, but like to me it was unclear. Like what is the like you I understand the problem statement, but what do the diagrams depict? What is causality here?
So these diagrams basically depict like, for example, if you take the purple color in this diagram,
Mm-hmm.
so it represents a particular type of bonding in your genome,
Okay.
and one particular like column of which comprises of different colors. It represents a like if you take up take like few 10 people from this community, for example, or stuff like that, then it represents one column, and the different colors represent the different bondings. So from that, you are trying to find out a particular like um if particular people are more prone to certain diseases or not.
Okay, so you reduce people to a set of whatever genome bonds they have, and then you correlate these genome bonds and predict the diseases they might have. Am I correct?
Yeah, not just diseases, but other factors as well. Like I mentioned, the metabolic levels and stuff.
Right.
So it is like kind of in a way taking a small subset of people, understanding their like genome structure in a way, kind of, and based on that genome structure, making inference about sort of like the possible diseases or like the characteristics that particular group share, like sort of in a way.
Got it. And the crucial, so reducing people to genome structure is done via Edward, and probably also the rest, but the rest can be done through other libraries also.
Yeah.
Fair enough.
I have a question. So, but hello.
Yeah, we can hear you. Go ahead.
Yeah. So I understood what you're saying, but I don't understand what this diagram represents. So, what are these white lines in middle? Do they signify anything, or this diagram
White
does
lines
not?
are just separations. Uh, White lines are just separating the different subset of people. And if you see in
Okay.
a particular column, so you can see brown, purple, blue colors, right?
Yeah.
So they are just types of bondings in your genome. So for example, if purple color, if you can see, it is like A going to B. So those subset of people have a large amount of purple color, which if you see clearly in the diagram, then one particular column also has many small columns, like they are combined, which is why you see the pattern. And they are basically each person, for example, if we take one person for example, and he has 80% of bondings as A going to B, then the 80% of his line would be purple. Then for example, blue would be B going to C, and if it is 10%, then 10% of that line would be blue.
Okay.
So like
Okay.
in a simple way, you can think of like as like let's say this particular line strip as sort of like representing the whole population in a way, and like the smaller columns as like sort of small age groups in a way, and like this for each age group they have some specific genome characteristics that kind of are highlighted in the group based on that color, and like based on that particular genome structure we understand what particular group has some disease or some characteristics like that way, and based on this particular like color map sort of like we try to understand like the effect of this particular genome structure and like the causality effect of genome structure and the disease or sort of characteristics that can be maybe, yeah, this would be like
Okay.
simple diagrams.
Okay. All right. Thank you.
Should I continue?
Yeah.
Yeah, so in this NBA case study, we have a data set which comprises of a bunch of individual points on the basketball court, and we want to analyze areas from where this NBA players are most likely to make good shots. So here, as you can see on the top first two images, we have two specific players whose data has been analyzed for inferences algorithms, and we are trying to find out the certainty with respect to how well they would make certain shots and from which positions they would make certain shots. But which positions they like they should shoot from in order to be more certain to like score. So then these are the images below basically show the analysis of the parts from where these players are likely to make good shots from. Yeah, can you? Yeah. So This slide is basically taken from Frank Wood, who is the leader of Anglican. So Anglican is one of the probabilistic programming systems, and this basically gives a historic view of probabilistic programming languages in general, and it shows that how they have converged to a particular area right now, and the area where you can find famous probabilistic programming frameworks like Stan and Church in this slide, and it basically gives you the evolution of these languages from time. Can you go to the next slide? Yeah, so George E.P. Box was the one who pioneered iterative process for science, and the library Edward is actually named after George E.P. Box's middle name, which is Edward. And basically, what iterative process for science was that uh, once you have a data, like you build a model from the data and you try to uh, generate a model from where you can find like inferences from the model. Then from those inferences, you criticize, as in you try to say that are these inferences correct or not and stuff, and then you try to inculcate those and again build a model. So from step three, you go to step one, and the process continues. So in the next slide, this is basically the loop, which is named after George E.P. Box. And this is what like said that first you do modeling, then you make inferences from it, and then you criticize. After criticizing, you again go to modeling, and this loop continues. So Edward is basically trying to inculcate this loop into its procedure, and it is using this to make inferences. So this is, yeah, the next. So Edward is actually available, like it is open source and it's available on GitHub, and it is a Python library which is used to do probabilistic modeling, inferences, and criticism. So it is basically used in the scientific community for scientific research on modeling and probabilistic programming, and it fuses three fields, which is Bayesian statistics, deep learning, and probabilistic programming. Can you go to the next slide? Yeah. So Edward, some facts about Edward is that it is Turing complete. What do I mean by Turing complete is that it can run any program which a Turing machine can run. So this is basically a matrix to find how generalized a particular language is and if it can do everything or not. And then, like I mentioned before, the main two goals of Edward are uh, that it wanted to make like a probabilistic programming as flexible and computationally efficient as traditional deep learning. What I mean by flexible is it tried to inculcate all it in, it try to make it easy to fit the same model by using various inference methods, for example like point estimate or variational inference and stuff like that. And by computationally efficient I mean is that Edward is basically integrated into TensorFlow, and according to its counterparts, like for example, Stan, it is at least 35 times faster than Stan, and it is also 6 times faster than PyMC3, which is so basically it can do a lot of things and it can do everything better than its counterparts. So in Edward, Edward defines two like compositional representations in two parts, which is random variables and inferences. And the main thing is that it treats inferences as like equal to modeling, and it incurs no runtime overhead, and it is as fast as like handwritten TensorFlow. Can you go to the next slide? So now related works and frameworks related to probabilistic programming. So they can be divided into two broad categories. One is the expressiveness of the language, and the second one is computational efficiency. So like I mentioned that, for example, church. it is good. It is good at doing a lot of things, but then it is not computationally efficient in doing all those things at the same time. So, in expressiveness, what we find is that we have generic inference engines, but they scale poorly with respect to data size. And in computational efficiency, basically the frameworks are good at doing one thing, but they can't do other things. For example, if you see InferNet, it is very fast in like message passing for graphical models, but and Augur, it is like very good at data parallelism with GPUs for GIF sampling. But can you go to the next slide? Yeah, so here we have few more systems like Venture and Anglican. So in Venture and Anglican, the main thing was that inference was designed as collection of local inference problems, and AdWord actually builds on it. But in like it is different from Venture and Anglican because it supports posterior approximations and inference models as well, which those two systems didn't support. And then uh, Edward also reuses the modeling representations as the part of its inference, which makes it computationally efficient. So, for example, Web PPL did not reuse models, the representation of models again, which made it kind of slow. So, these were the differences which Edward had from the related models. I think Jay will continue from.
So now coming back to modeling sort of. So here like we all know in TensorFlow also models are basically an computational graph where like basically the nodes represent the operations and edges represent the data, and basically here we build a graph and we execute the graph at the end part here in a way. So Edward also augments the same particular ideology sort of building the computational graph here, but here in this case the only difference is sort of it uses with builds a graph with abstraction of random variables. So your random variables are basically, in a way, you can think of it as a object, TensorFlow object or tensor only, with some basically wrap with some parameter like class object, like in a way. So that is basically, or you can think of like a random variable that is an object parameterized by the tensors, theta, or in a way like sort of. So here basically for writing this Edward model. So here we can see some demo. So like for univariate normal, we basically mention the location and the scaling factor. So that is the mean and the variance. And for vectors, basically of phi univariate, we basically represent it in terms of vectors, like we initialize with vectors. And for 2 by 3 for matrix, we initialize it with matrix here like that way. So here basically the Edwards model basically has sort of some peculiar features like compared to TensorFlow, no, tensors, normal tensors. So here it has sort of explicit methods in a way such as log probability and sample, which can carry out explicit density method sort of like that way. And here basically you can think of this implementation as like TensorFlow. All it is similar to TensorFlow only, but just here it is wrapped in a way and all basically wrapped to associated tensor and like has some additional methods in a way. So here you can think of like a random variable for associated to a tensor x asterisk as like basically drawn from a probability distribution of the observed variable x given the tensor basically a theta star in a way like the distribution sort of in a way. And if we see now like two-layer neural network, like a feed-forward neural network in TensorFlow. So here we take the inputs, weight matrices, and we multiply the weight matrices and apply Tanish linearity, non-linearity, and basically pass it on like, and we get the particular network here defined. So like, how would we do the same in Edward? So in Edward here, basically we have this particular random variable models basically. So here in this case, we initialize the normal distribution. So here with the mean and the variance of respective dimensions. So like taking d-dimensional features and like outputting the hidden size here in a way, and then passing on same as well, like going for the weights as well and the biases here. So this is a bit of analogy of how TensorFlow and Edward are related in a way. sort of. So yeah, Josh.
Hello. Yeah, so this is a example of beta Bernoulli model. So basically, you can think of this as modeling 50 coin flips, where, for example, zero is heads and one is tails. So we can find, so here, as you can see in the equation, so x is a random variable which is 50 dimensional, and theta is the latent probability which is shared across these 50 data points. And we are basically multiplying all the probabilities because we are considering these samples to be IIDs. So as you can see in the computational diagram here. So from theta, we sample and we find theta star, and then we share it across 50 data points. Like TF dot 150 is basically a vector of length 50 whose all elements are 1. And then we find X and we sample from X to get X star. So in the code sample here, you can see that we are first setting a beta prior with hyperparameters, like the ones in the bracket A and B, those are hyperparameters. So, and then we are finding Bernoulli likelihood from the vector of length 50 and multiplying it with theta.
Okay. Just a minute. Okay. So coming to variational autoencoders now. So like let me explain first what is a variational autoencoder. So like you can consider there is sort of some observed variable or like the data here x, and we want to find the distribution of that x. We don't know exactly how the data is being generated. We want to find out the data generating process in a way. So here we assume that there is some hidden variables sort of or unobserved variables like let's say the basically z, through which basically your with the distribution which basically comes from a distribution queue, and basically this distribution passes through a neural network and then generates the actual observed variable x here, like so we get the actual data in a way. So you can consider the encoder part as like basically getting from input data to the hidden variables or the unobserved variables, and the decoder part as getting from the hidden variables to the exact data, like basically generating the exact data in a way sort of. So here basically for the encoder part, basically we assume that the hidden variable is basically drawn from a normal distribution with mean, mu, and sigma, sort of like here. And here basically this is the condition on the distribution phi here. So and for like the uh, decoder part, basically we know that this particular distribution hidden variable z have been drawn from normal distribution, and like we basically for all the d dimensions, and then we basically here use it as a Bernoulli. Here the reason for using Bernoulli is basically we are generating the binarized MNIST, so that means here the value for each pixel is either 0 and 1, like that way. So which is why we are using a Bernoulli distribution in a way, and basically here the probability is basically defined by the normal neural network of that z comma theta, basically your parameters by the theta. If any doubts like for variational autoencoder, like anything?
By binarized MNIST, you mean just zeros and ones?
Yeah, in binarized MNIST, like the pixel value for will be basically 0 or 1, each pixel value in the image. So here we are basically generating like the pixel values like of a sort of a d-dimensional representation, let's say, and basically for each basically represent by what I mean position, we are generating either 0 or 1, like that way.
Right, but the numbers are still 0 to 9. Like the images will still be of numbers from 0 to 9. It's just
Yeah,
every pixel is either 0 or 1.
yeah. Like categories are still 0 to 9. Yes, just the pixel values are like for the image are basically between 0 and 1, like so instead of 0 to 255 sort of.
Sounds good.
Okay, so now like basically let's see how we can basically code this thing in Edward, or like write a code snippet for like a model basically here in Edward. So here like basically probabilistic model. So this is basically the data generating part, like the decoder part. So in this case here we basically assume that Z is drawn from a normal distribution. So this is our prior, like, so we assume that Z is drawn from a normal distribution in a way with the mean zeros and variance one. So we define it like from a matrix of n by d dimensions. So that means like the n number of examples and the d dimensions for each of the example in a way. And then basically we pass this Z through a hidden layer. So that is a dense feed forward. We can consider normally feed forward layer in a way. So that is a 256 representation, and we use activation ReLU here. And we then pass this hidden representation here like that we get through a Bernoulli distribution, where we pass the logics here again through a hidden layer in a way like sort of a the dimension 28 by 28. So this is basically the data generating part. Now let's understand basically sort of the variational part, like the inference part, sort of like, so how do we get the particular hidden variable Z given some data like we have X. So here this particular, like the hidden variable Z is basically defined by the distribution phi. So in this case here we put a placeholder like of TF using TF dot placeholder for a dimension, basically with the dimension in comma 28 by 28, because the pixel value for each image is 28 by 28, so it's 784 like flattened image sort of in a way, and n is the number of examples in a way. So here we define this particular immutable state here in a way like which is the actual data. Then we pass that particular actual representation here through the hidden layer of dimension 256 and activation ReLU. After that particular getting the hidden representation like calculate value, we pass it again with the normal distribution here, where we define the mean and the basically your variance using a neural network here. So the neural network has d dimensions in a way, and here we use the activation soft plus for the variance part. Any doubt so far? So this is how like we do auto variation auto encoder basically in Edward sort of. So there's like 6 lines of code define the whole model in a way. Should I move or like any doubts?
Sounds good to me.
Okay. So this is again like another example, that is the Gaussian process classification. So here you can consider this as a supervised learning task. So where we have a paired input. So like basically of x comma y. So x is the input and y is the output here that we get basically for that particular corresponding input here x in a way. And here we want to classify the particular given some like basically input data x. What would be the y value for? What would be the categorical distribution of the output in a way sort of. So here we use the Gaussian process. So here the Gaussian process are nothing but like we are basically assume that the classification in a way for each class there's sort of a Gaussian distribution in a way. So which is defined by mean and like some this is defined basically by some mean as well as variance in a way like so that distribution. And here basically again, so we define a declare basically a immutable state say TF dot placeholder, which basically takes a n by dd matrix. So where n is the number of instances, d is the number of dimensions of that particular input, and then we basically pass it through a multi lower triangular multivariate normal here, so that we assume sort of a distribution like a prior distribution sort of like from where this particular uh, like the classification distributed are like basically sort of, and basically it is also defined with mean zeros basically a vector and a scaling factor in a way like variance. So here tf dot Cholesky factor. So here in a way the Cholesky factor is nothing but like it is basically used for Cholesky decomposition. So where we have a square matrix, specifically positive semi-definite matrix, we decompose it into two matrices, like the product of two matrices, which one is like the lower triangular matrix and other is the conjugate of that same lower triangular matrix. So here basically we define that decomposition in a way, and basically here for that decomposition we pass on some user implemented RBF kernel like from which like the input is processed. And then again basically as usual we pass this particular hidden representation to the Bernoulli and like basically classify it. So here again in this case it's a basically a binary problem, that's why we are using a Bernoulli classification in a way. Any doubt? So this is sort of a like simple setting for like Gaussian process classification. You can think of it as a, like on a higher level as a supervised learning basically problem like where we class Okay. Like we find out the y given x number, basically in a way, for that data. So now comes the another application that is known as latent digital allocation. So here this application is specifically used for understanding the topics here basically over the documents. So the basic idea in a way is like there are D documents, and for each document there are n number of basically your words per doc. So they're like basically let's say there are D documents and like each document has some n words in a way. And here for each document also like we have some top like each document also have some topics here. So like on a higher level you can consider it as like documents composed of some topics and topics composed of some words like that way. So this is usually represented using a plate diagram. So here like we have a d-dimensional d documents, and for this d documents we have sort of a k topics, and for this k topics we have like n words, and here we assume that the for document like basically the theta d represents here the per topic document classification, so sort of distribution from where the topics come, and the phi of k represents here the per topic word distribution, sort of like the for each topic like the distribution of the words from where the words basically come from like that way. And here for which basically we assign some priors for both distribution, that is a theta d and phi of k. So like here this is a prior sort of like initializing a matrix of zeros of dimension d by k for basically the per topic document distribution, and like here the uh, zero matrix of zeros of dimension k by v for basically per topic word distribution. And then basically for each of the document in a way for we go through the basically your words and we define the categorical distribution. So that means here for each of the document here we find out the topic for that particular word, like basically so we find out the topic d for the init word in the document d, and for that particular the topic here we find out the word like the specific word that belongs like. So this is basically used for understanding the topics as well as generating in a way you can think of it as like a distribution from which we understand like where how the topics are and documents are basically in a way based on the topics and the word distributions. Any doubt? So yeah, categorical basically is nothing but like since this is a categorical distribution, sort of like we have a vocabulary fix. So from where like basically the words and the topics are drawn, so that's why it's a categorical distribution. Any doubts or like should I move forward?
Oh, I've got a question on the previous slide.
Yeah.
So you're talking about two different examples, right? In this one, are you like trying to get point estimate value on here? Is your prediction is like a point estimate?
Yeah. So this is a point estimate value in a way like, but
Your output is from Bernoulli, right? But
yeah, output is
you're
Bernoulli.
getting
So
a
it is point
distribution.
estimate. Yeah, it is a distribution, but like basically having 0 1 values, right? Means like it's a binarized basically it is classification problem. So we get a distribution in a way like, so Bernoulli is just basically in a way like sort of a for binary sort of a output, sort of you can think of it.
Oh yeah,
It is sort of a distribution, so it is not exactly a point estimate. Like we get a distribution in a way like sort of a spread around it, sort of, yeah. So like the error bounds and the uncertainty like of that particular prediction.
Yeah, right. Like Bernoulli would give us like it would have only one turn, like it's only have n is equal to 1, and it would tell you whether it's a probability of success or failure, right?
Yeah.
So from there, how are you gonna make out what the uncertainty is?
Yes, this is a good question. If someone knows, like, feel free to jump in.
After you make, after you run the code, does it, are there like parameters that you can access that maybe will help finding that. Uh, I don't know. There must be, because I was also having a similar doubt. Like after you run this, you get the distribution, but like how do you know what the distribution is?
So like in this case, we initialize sort of distributions, right? And we like some prior distributions, and we update our beliefs based on the data that we have seen, sort of. So it is updating distribution, and you get the exact distribution, right? After like sort of like the approx distribution to the true distribution after running like through the training data, updating the parameters. Like so, that's the point of probabilistic programming, right? You apply kind of update your beliefs based on like the evidence that you have seen so far.
Yeah, but the question is, how do you get to
Yeah,
uncertainty from your
yeah, yeah.
probability distribution?
Uh,
I think the answer is to go one step back. Like you don't always get zeros and ones as predictions. Like you typically set thresholds and then you squash your predictions into zeros and ones. So if you don't do that, then at least you get an uncertainty estimate with respect to how far it was from zero before you squashed it.
yeah, yeah. I think that would be a good idea to put it.
So if you think of the regression problem before that classification threshold is set up, it might make life easier to think of where to get the uncertainty from.
Yeah. So basically, in a way, like we define threshold, sort of like the boundaries around which we want our data to be, and based on that, we kind of get the final estimation. Like, so basically, we kind of know in a way like what kind of uncertainty levels, like, or basically sort of in a way the confidence interval levels, like we want our data to be like. So based on that, maybe I don't know
So,
if this is a good
so the
like answer, but
question, sorry.
yeah, but yeah, sorry, one second.
No, no, complete your thoughts. Sorry.
Yeah, I don't know if this is a like proper answer exactly for this, but probably like after the presentation, I will find out and like maybe share some thoughts about this. Yeah, but I think the idea is basically you're kind of restricting like the thresholds in a way, like so based on like the kind of boundaries that we define. So, like for some examples, like we want our uh, error to be very small or like sort of in a way boundaries are very restricted sort of. So based on that, like we then kind of get the final output estimation, like clipping off and like doing that things.
I just wanted to add, I'm not an expert on Gaussian processes, but it seems to me like it's like a function over functions.
Yeah,
And so, like, the the thing you're trying to fit is to restrict the space of functions until you have something that describes the data generating process. So like in the XY case, it's fairly simple. Like your X's are on your X axis, your Y's are on your Y axis. So you want to find a function that like predicts this X to Y correspondence perfectly, but it doesn't seem like you can do that directly with Gaussian processes unless like you want, because it's like ultimately what we're looking for, a Bernoulli Y, right? So if Y is only zeros and ones, then a Gaussian process by definition cannot be the correct model, but like it can still do reasonably well. This is again, this is my thought process. I don't know if this is the correct explanation, but if you're like, I don't know if you can imagine it, like if it's a 0, 1 value, and if you're fitting a continuous function to it, there is going to be some approximation somewhere, right? So using that approximation, you can get those uncertainty intervals of, okay, where was it very close to one and we predicted one, where was it not that close and we predicted one, that's greater uncertainty. And so at least that's the way I would think about it. I posted a link to the exact tutorial that they're talking about. But yeah,
yeah. Like, no, otherwise, like we also find it out like after the presentation as well and put it
yeah,
on
we
the
can we can
Discord.
definitely talk about that.
Yeah, yeah. This is a bit, yeah. This is a good question. Like,
Yeah, thank you. This was a great question.
so any doubts on this like LDA, sort of like how we do it? So I think we can move forward. Yeah, Deep can
Yeah.
take over.
Yeah. So now we'll be moving on to inference and how the authors of the paper have introduced various classes of inference in Edward and what do they really mean. So, like, can you go to the next slide? So yeah, so the most important thing that we have to first understand is what is inference and how does it stand with Edward. So if we imagine that all of us have already experienced scikit-learn, right? So for what happens with scikit-learn is when you go to fit a model, you have two different methods. You have scikit-learn.fit and the other is model.predict. So these are two different methods. But with Edward and with Bayesian inference, in Edward, what happens is that they don't have a distinct model or inference block. And the second sentence of the first point, as we can read, is the most important thing that we have to know about inference. So, as I quote, a model is simply a collection of random variables, and inference is a way of modifying parameters in that collection subject to another. So basically, what we learn is that a model is made up of various random variables, and inference just modifies it based on the parameters of the distribution that we are trying to infer on. So this provides a plug and play capability to Edward. So what that means is that, for example, we can use Edwards for only certain parts of a model in order to infer from them, such as layer-wise training. Then we can use it for multitask learning, and we can also plug in a posterior into a new model. So what a posterior is, we'll be discovering ahead. So, like, can you move to the next slide? Yeah, so the authors have just made an introduction here about what really does happen in inference. And so we are provided with two different latent variables. So if somebody doesn't know, latent variables are observed quantities that are already known, like not observed, but you could say prior, but not exactly prior. So they kind of proved variables that you use in your distribution along with the observed data in order to get a prediction. So now and we calculate posterior distribution for inference, and this is a very kind of like dangerous looking equation. So we'll just skip this and I'll explain it in simple terms ahead. Could you go to the next slide? Yeah, so what is posterior distribution? Go to the next slide. Yeah, so posterior distribution is exactly what you can see in the red lines below. So it is using a prior distribution and a likelihood function on new evidence. So that is a posterior distribution. Suppose you have some prior evidence, and we'll see how to calculate this with an example next. But you use a prior distribution and you use a likelihood function on the new evidence. Now, this likelihood function can be anything. It could be a maximum likelihood function, a maximum a posteriori, or anything that we want. And this posterior distribution is what summarizes the data that has been already observed and the likelihood of the new observation that is to occur. So let's go to the next slide. Yeah, so let's understand what posterior distribution is with an example and how important priors are for the calculation of a posterior probability and a distribution. So the example is taken from from a chapter written by Professor Brian Junker at CMU. So the given quantities to us here are that a woman has to conduct an accuracy test and she has to determine that if the test is positive, what is the probability that she is actually pregnant. Now, now the given probabilities to us are that the accuracy rate of pregnancy test is 90%, 0.9, and false positive results are 50%. So, which means that 50% of the times, whenever a result is positive, it is not really positive. It is just an error on the test end. So like, let's just wait here. We know these probabilities and we don't have to do any calculation. But could any of you answer, like, what do you think intuitively, approximately, what the real probability would be of the woman being actually pregnant if the test shows positive? Like, you could specify a range or anything, and like, there is no wrong answer here. We'll just understand how important priors are if anybody wants to attend. And like, please don't go to the next slide and see the answer. uh, Anybody can attempt it.
Yeah, just based on your intuition. Like,
Yeah, just based on
tell
the
us.
intuition. Swapnil, would you like to try, just on the given data?
0.75.
0.75. Does anybody else wants to try? Like, there is no, I'm not forcing anyone here. It's just like people could get involved.
So what they're asking you is simply that, okay, this is a problem setting where pregnancy tests are 90% accurate and there are 50% false positive results. So what is the percentage chance that you are pregnant given that your test is positive? Just a guess. It is based on no calculations, just a guess.
0.8.
Okay. So like, yeah, go to the next slide. Yeah, so the most important thing that I did not provide here was a universal probability of a woman being pregnant. So that is the most important prior that you are going to need while calculating if the woman is actually pregnant or not. And the authors calculated it as 0.15, and that prior played the biggest role, and the probability of the woman being actually pregnant was just 0.241. And the formula you can see here is just a basic Bayes theorem to calculate the real probability. So like, we went from 0.75 and 0.8 to directly 0.241. So as we see, priors are pretty important in this setting. But now here's where the real problem starts. Now, suppose the woman taking the test is a statistician, and she knows that this problem can occur while taking priors. And what the real problem is, we'll see in the next slide. So could you just switch? Yeah. So if the woman is aware, now the new updated probability of a person being actually pregnant is 0.241. It earlier it was taken as 0.15, which was a universal arbitrary probability that they got. Now, if the woman is not convinced and she decides to conduct 10 tests on 10 tests repeatedly, updating this probability. So the probability 0.241 is also called as the posterior probability. That is the updated probability that we got after one test. And as we can see in the second point, that after another test taking the probability as 0.241, she gets that there's a 36.4% chance. And as she reaches the 10th test, we get that there is a 98.4% chance of her being actually pregnant. Now, this is the major issue of concern in Bayesian statistics, as you don't know what prior you are going to use and if it would actually help you achieve global optima or not. And that is what the authors expressed concern in while explaining why they need to calculate, why they need methods better than posterior probability in order to calculate these. So, does anybody have any doubt up till here? Like, do you not understand posterior probability or any other term? Okay. So let's. Jai, could you go to the next slide? Hello. Am I audible? Yeah.
Yeah, yeah, I'm on next slide only.
Yeah. Sorry, get updated.
Classes of inference.
Yeah. So classes of inference. So the author conducted three different inference experiments in order to test how Edward performs on each of them. So the first one was variational inference. So variational inference, as Jai explained earlier, it is that you have a family of distributions which are nearby to each other, and you have to find the closest member in the family, given that you have a posterior already. So it is basically you can if you want to visualize it intuitively, you can say that you are trying to do a k nearest neighbors algorithm on various distributions instead of the points. So that is a very loose explanation of what variational inference is, and we'll go into detail next and how it was explored further. The other one was Monte Carlo. It was actually the Hamiltonian Monte Carlo, and it utilized the maximum a posteriori, and we'll also discover what this is ahead. Like, I'm just introducing everything. And the third one was non-Bayesian methods. So what the author stated that even in non-Bayesian settings, we could use Edward in order to generate inferences. And for these, they explained an example of a generative adversarial network in which they used to feed a noise into the generator, and the neural network and the authors built an inference in order to optimize the parameters. So basically, you take out the inference part of the GAN, and you kind of fit the Edwards inference engine. Like, as I said earlier, there's no inference engine in Edward, but Edward is a plug and play framework. So you fit the inference part in between the discriminative network and also in between the generative network in order to introduce Bayesian inference in this. And that is a basic example. We're not going to go into much detail there. So, like, could you go to the next slide? Okay. Before going into variational inference, now as we explored that what variational inference was, so whenever we are about to go into variational inference, the model that we could always think of would be a variational autoencoder. Now, Jai has explained variational autoencoder in detail earlier too, and in a previous session. But if anybody didn't attend, I'll explain it in very short. So what you do with a variational encoder is you take data from an image or anything, and you map it onto a latent distribution. Basically, you encode that data onto a latent distribution, and that is the encoder part of the variational autoencoder. And after that, in order to decode that, you use a function in order to decode or reconstruct the data from that latent redistribution. And in order, so basically, it is a generative function, and we'll explore how we conduct various the encoding and the decoding. For this paper, what the authors did was they used various inference methods. So they used various models conducted on the binarized MNIST that Jai explored earlier. So now, the four best performing models, as we can see here, was the original variational autoencoder with the KL divergence reparameterization trick. Now, they removed that and they got a slightly worse result. They used analytic entropy in place of it. The result degraded, and they used a score function gradient. Now, we'll just be exploring these four in detail as they are the top four in terms of results. Now, going on to leaving the one that is the original one and going on to the other three, the number 2, 3, 4, without analytic KL and everyone. So what we explore is that all of these methods, the analytic KL, analytic entropy, and the score function gradient, all of these have the same achieve the same global but they do so at different convergence rates, and that was the main issue that the authors tried to go through. And they achieve different convergence rates because the tricks used for performing the calculation of gradients are different in these, and we'll explore what they are. Just go to the next slide. Yeah. You can skip this one. This just explains what the different models are. I explained that. Yeah. So the three that we didn't explore in detail. So the first one is VAE reparameterization without analytic KL divergence. Now, first things first, if somebody doesn't know what KL divergence is, the most intuitive way to understand KL divergence would be that you imagine two distributions that are overlapping each other, and you calculate the area which does not overlap. That is what KL divergence actually is, and it means a relative entropy, which is the difference between cross entropy of two distributions and their own entropy, and which is exactly what we calculated intuitively, the area under the overlapping areas. So the analytic KL was a trick used by the original authors in order to do back propagation. So could you just go to the next slide for a second? Yeah, so this is a diagram of you see the right one with the epsilon in there. So the epsilon was used as a stochastic node in order to do back propagation in variational autoencoders. Now, since the authors don't use the traditional cross entropy in variational autoencoders, they tried to use this in order to get non-deterministic results, and the formula, as most of us would be familiar with, would be is that the new distribution is calculated with as the mean of the current distribution plus sigma into epsilon. So all of these terms are visible here. So sigma into epsilon are multiplied, and the new distribution is calculated using that. The what the authors did was they removed this KL divergence trick, and they tried to use the probability decoder, and it performed as the second best one. Just go to the previous slide again. Yeah. So the next one was the analytic entropy. What the analytic entropy did was it was very simple. Like, instead of using the KL divergence, they used the simplest entropy formula in order to calculate the varying entropies in the system. And now coming to the score function gradient. So in a paper proposed by Dr. Rajesh Rangnath and et al. Called black box variational inference. They needed to compute the gradient in that in order to perform variational inference. Now, in order to do that, they took a Monte Carlo estimate of the gradient from a sample Q, and that is called the score functional approach. Now, how do they take Monte Carlo estimations? We'll be discovering ahead. So, like, could you go to the next slide?
Just to clarify or add a point in this case, like for this particular like original form, why it doesn't work, sort of. So for back propagation, we don't want like stochasticity, sort of, in a way, like sampling sort of processes in between the nodes. It is okay if they are at the input level or the output level, sort of. So we try to eliminate that by introducing some noise parameter epsilon, which is like sort of a stochastic way, and basically that is basically used for this particular generating the data latent space, and then we are able to do the back propagation. So this is like a reparameterization tick, and why the back prop works in a way.
Yeah, thank you for
If any
that.
doubts, or like, yeah.
Like, does anybody have any other doubts?
Any doubts regarding that back propagation, sort of, or
Yeah, or
reparameterization?
any other methods that they use.
Yeah.
Okay, so I'll continue. So the other method that they used was the GPU accelerated Hamiltonian Monte Carlo. So as you can see in the diagram here, this is the same diagram that Jay explained earlier, the beta Bernoulli model. And what they did additional here was they introduced an inference step using the Monte Carlo sampling, and then taking a point out of it using the MAP estimator. So like I'll explain what each of these mean on the next slide. Could you just go to the next one? Yeah. So suppose you've been given a probability density of px, and you need to sample some data from it. So the Hamiltonian Monte Carlo is the same, that it generates gradients on a Markov chain in order to sample data. Now, basically you can just imagine it as normal sampling, but happening with the help of a Markov chain, and all of this is based on a gradient. Now what happens here is that the input or the observable parameter x, it must be unconstrained, so it could be any real number, and if you want to clip it to a specific distribution, then what you can do is you can, the constraint data should be mapped to a particular distribution in order to calculate the Hamiltonian Monte Carlo sampling. And after this new distribution is sampled from the Monte Carlo sampler, we calculate a maximum a posteriori point. Now, what is maximum a posteriori point? So it involves calculating a conditional probability using the prior probability of the model. So basically, it means that you have a model that you bring a data that you have a model and you bring new data to it, then you have to calculate a conditional probability of any result that you need to obtain using the data and the model that you already have. Um, that, like, did anybody not grasp it, or does anybody have any doubts, or if somebody thinks they can explain it more clearly, then you're welcome to do so. Okay. Could you go to the next slide? Yeah. So the authors conducted a large-scale logistic regression using this engine of the Monte Carlo sampling, and what they observed was that with using all the different frameworks that we discussed earlier in the slides, Stan, PyMC3, and everything, and what the authors observed was that on a GPU setting, Edward worked as fast as handwritten TensorFlow, which means that there is no overhead in using Edward in place of other already established frameworks, and that it is optimized at a really core level. So that was a big win for the authors who wanted to spread like increase the usage of Edward, and also while introducing new functionality, this would be useful to get it to scale. Could you go to the next slide? Yeah. So the last inference type was the compositional inference. Now, what compositional inference does is a mixture of the two that we discussed earlier. The first one was the variational inference, and the other one was the Monte Carlo sampling. So what this does is first, we calculate the two latent variables as observed in the code, which are q beta and qz, and after that we make the first inference method. As we see, the inference E is for variational one and M is for the Hamiltonian Monte Carlo one, and after that we run a loop. So what happens here is that whenever the variational inference updates the latent variables, those latent variables are then used for the MAP function. So basically, you're running two different inference methods in parallel, and you're also mixing their results in order to produce an overall better result. So you could assume this as an ensemble of the two inference methods that we discussed earlier. And this could also be used in the same way that the others were being used along with the core TensorFlow. I think Josh is going to conclude now for the next slide.
Yeah. Is the next slide visible? Yeah.
Yeah.
So, like I mentioned before, the main goal of Edward was to expand like the scope of probabilistic programs and make it as similar to deep learning methods in terms of flexibility and computational efficiency. So, Edward tries to address this Edward tries to achieve flexibility by showing that like it can use a variety of inference methods, for example, like point estimation, then Markov chain Monte Carlo methods and stuff, and it can even capture recent advances in BAEs and GANs. And for the efficiency part, it showed that like how Edward used computational graphs to achieve fast computation, and it scaled well to massive data as well. And like I mentioned before, that it is 35 times faster than Stan and 6 times faster than PyMC. And can you go to the next slide? Yeah, so Edward basically makes certain trade-offs in like order to achieve its goal of flexibility and speed. So there are basically two open challenges in Edward. The first challenge is to like better facilitate programs with complex control flows and recursion. So it is possible to represent those programs in form of like complex flow structures, but it is unknown how to devise flexible inference strategies for those programs. And the second open challenge was related to computational graphs. So, like we saw in the examples before, like all computation was represented in form of graphs which basically helped us to leverage the model structure during inference. So now the challenge is to expand this design like to inculcate dynamic graph frameworks as well. So if it is done, then it would provide more flexibility and like, but it might hamper the performance. And now the Dustin Tran, which is the like leader of Edward, is working on Edward 2 right now, where he is trying to address some of the shortcomings and open challenges. And he is even applying Edward as a research platform for developing like new probabilistic models and new inference algorithms. I think that is it.
Yeah, like feedback sort of questions, anything.
One
Yeah,
question.
if
Um, it's on the Hamiltonian Monte Carlo. Why did they use Hamiltonian Monte Carlo like specifically over other MCMC algorithm?
It was the Hamiltonian Monte Carlo was used as a demo method. They just wanted to represent. So it was basically a demo that they were trying to show how fast the system works. So you could use all the other methods. The Hamiltonian Monte Carlo was just an example in order to demonstrate how it fits with the other models and how fast it could
Yeah.
be.
So it is sort of an example of like data subsampling, like which is used for mini batching, and like how can you kind of parallelize like the model training on GPU sort of. So you can also use other like MCMC techniques like that way too. They
Yeah,
just use
and
like Hamiltonian Monte Carlo, like
yeah,
basically
even
that's the
for
main point to
calculating.
us. Yeah, go on. Sorry.
Yeah, no, I was just saying that even for calculating the estimates, instead of MAP, they could have used MLE or some other method. So this was just an example that they used, but it is like really easy to use the others in place of this.
Yeah, but main idea you can take a sort of like the data subsampling, so it kind of enables us to do mini batching and all that things, and like kind of doing data parallelization and all sort of computation. So like yeah, you can use any other like samplers as well, like kip sampling and all too. I think yeah. Swapnil, feedback, others as well. Like
I have a bunch of feedback, but I'll wait for others to give you like it's good practice also to critique a presentation.
yeah,
Um, so I'll hold off.
and like most of the examples that we explain, like so they have like demo or tutorials on the website, but like unfortunately like that Edward version supports TensorFlow 1, so like yeah, now there are few models which have been completely removed sort of, so it doesn't work sort of. So yeah, you could try that same demos, maybe like modifying a bit and working out with Edward too. It's sort of similar to the Edward one in like structure and like that we do. So yeah.
Okay. In that case, I can get started. So, couple of things. The famous in a way resurfaced many times. So, keep track of that. Because you're explaining exactly the correct thing. It doesn't need an inner way to be said. Um, but yeah, so the good thing was for Jay at least, you explained things very well. Your concepts are clear in your head. Now the work needs to be done on conveying that in few words. So
Okay.
that elegance, I think, comes with firstly practicing paper writing, and
Okay.
secondly like with time, like the more you talk about these things, the more confident you are and the easier you can explain like this whole latent variable modeling data generating process, like what are these things, why do we care about them. Yeah, so that's for that. Reasonably good. For Josh's part, if you put in all the hard work on analyzing these references just to make that one slide, then you probably want to make people ask you questions and convey that knowledge to them. Otherwise, you're being inefficient. Like you spend all this time on it, and people won't realize that unless like you tell them, okay, ask me questions about this example, or like even better, like ask them questions about this example. The presentation was clear, but the slides could do with more detailed labels for the diagrams. Just as a, if someone looks at the slides later and they don't have your presentation, they should have that in hand to understand what the slide says.
Okay.
Inference as a first class citizen, I don't think that came across in the examples, but like just when you explained inference as a first class citizen, it would have been nice to have like one example of like here is like regular code and like standard deep learning as you explained, and here is inference as first class citizen. Um, uh, anyway, that maybe that's a bit too much to ask. The slides are extremely clear, so good job on that. Part three. So I tried to name the people who were presenting, but there are so many switches that I forgot who was saying what. So I named it in parts. I think part three, well, but part four was deep. Okay, I don't know who part three was. Whoever explained the code examples, good job. You boiled it down to core ideas instead of sticking to jargon, which is usually very hard to do. But yeah, good going. The key piece of feedback is if you introduce new topics as parts of these examples, for example, Gaussian processes, you have to be sure to have like a 5 line intro with like tying it to concepts that people are aware of. So Gaussian processes, function over functions. You should like know what you're talking about it to that level. Like you don't need to know Gaussian process research directions, but that would be nice.
Okay.
Part four, presentation was extremely clear. Slides were very verbose. I think this was deep. I really loved the interactive discussion. The fact that you asked the audience a question and made them answer, and it wasn't a question you had to be like you had to know things to answer, but it was a question that made you like participate. That was a very good thing. And you explained starting from the ground up to explain concepts, also a very good habit. Like overall, this was like a very good quality presentation, combining all three of you. So yeah, that's my feedback. It's also on Unicode research meeting notes, so you can refer to it later as well.
Okay.
Like, did you feel we could have added more info about anything, or we missed out of any stuff that was important?
I don't particularly think so, partly because of the audience. Like, this audience couldn't take away more than what you said. Yeah, I guess for a more academia oriented audience, you want to tell them about how they can use probabilistic programming in their field. So you want to lay more emphasis on these examples that you provided, in terms of, okay, but what else can this do, and like propose ideas. But again, that's like an academic audience. This is not completely an academic audience. Like, we're also practitioners. So from that perspective, you were at the right level of detail. Yeah, that's a good question. I don't know what else you could have covered.
Any other feedback as well, like others? Yeah.
I'm sorry, I couldn't hear you.
Like I'm saying, like feedbacks from others as well, like would be appreciated.
Oh yeah,
What they
please.
feel. Yeah.
Yeah, this I really liked the presentation, and the slides were also self-explanatory. But regarding the examples part, I would have liked more discussion around those, because those
Okay.
why did you present those examples? What was their impact? Why the problem that those examples were solving is important to anybody, or important to us, or important to the people who solved it, and more discussion about that, and some details about that on the slide. So you had a big diagram on the slide, and
Yeah.
you were kind of trying to explain what the slide was. So instead of that, if you could have some pointers that what was the outcome of that slide, then it would have been good. Yeah.
Okay. Yeah.
Rest of the things, I think they were good.
Okay.
Yeah, same. Matlab, I'd say it was actually matlab, very clear, and I especially like Deep's part very well. He went into, he came up from he explained everything from the ground up, and that was very helpful. As far as the programs were concerned, it would have been really, really good to see the output as well. What Kushal just said, that would have been perfect. Like, because I was able to understand what the program was trying to do, but I wasn't like tangible, what were the tangible results of that code. I wasn't able to clearly sort of get that from just the what the what the code was. But I think that would have required you guys to actually run the stuff, so maybe that was too much. But
Like
yeah,
we
Actually,
were
yeah,
trying that, but like that library
it is broken in
there was
TensorFlow
the
only.
so yeah.
oh
So
if
that was the issue. Like otherwise we were going to show demo as well, like sort of for the examples.
yeah, it
But
was
yeah,
still
probably we'll try to
very good. Yeah,
do it on Edward too, and like in our free time, and like let's see.
yep, sure.